Hello, everyone. Welcome to the sixth week of the Stefanich-Tannaka Seminar. Today we have Swaminathan Rajagopalan from Münster, and Swami is going to talk about completed relative tensor products. So, Swami, please take it away.
Yeah, thanks. And it's really cool to be part of this seminar. As all of you know, we've been doing a lot of technical, ingredients and prerequisites for the last few weeks. And today is maybe a little less technical, but it still is technical. But I will maybe start with uh, I'll just first start with my pen. So first, I'll just start with like why we're going to talk about this. Um, so as you all probably know, for Tanaka duality, we want to make a statement about like q co of x. So we want to consider q co of x for x a geometric set, and notably we haven't really talked about this yet. But so from the introductions and what I've read, I it seems like so the approach of this is to the approach is to consider a certain uh, uh, so it's called 2q co. Uh, so this is like quasi-coherent sheaves valued in growth and equally stable categories. Uh, in growth. And one of the next things we'll be doing is to like talk about uh, some global sections for a certain subcategory of this. So um, to talk about uh, global sections of 2q co BST comp X, where the comp the subscript comp indicates that we are considering those which are valued in complete growth in the pre-stable categories. Um, and one of the examples of such a thing will be I can't see the pen. Yeah. Uh, in particular, QCO X, the connective part of this is in growth and we want to when talking about global sections, we want to look at like this following category. So mod of QCO XEM in growth. So this is where our target is, and like I'm pretty sure the next few talks will say all these precisely. But the goal of today is to uh, establish a symmetric monoidal structure on categories like these. So that comes from a little more um, general like construction. So QCO X CN is an example of an admissible algebra in growth. And uh, so today's talk is going to be about admissible algebras. And uh, I don't know why the name admissible is coined, except for the fact that like it's only admissible to think about relative tensor products in these. And these are like roughly these are these have well-behaved bar resolutions. Bar resolutions and are the stuff we want to take, are these algebras are those which we want to take relative tensor products over. Right. Okay. So so much for the big picture. So I'll get into the talk, and thanks to like everyone who's presented before me, the proofs and everything are like quite simple in this, because I will often be just saying like we refer to so and so fact, and I mean because like the formalism has been like, I mean, it allows us to say this. So I mean, so sort of important for this is recall. So a couple of weeks back, Alex was talking about this two category growth ST comp. So we have uh, symmetric monoidal two categories, uh, growth ST and growth ST comp. And in the objects of the first guy, uh, the objects of growth ST are given by, a tuple of like the following kind, where C is growth and decrease table. Uh, and the comp is of course a subcategory of this. Uh, uh, growth ST comp is the full subcategory uh, of uh, objects. Oh, sorry, with objects uh, of the above form, of course. But you ask that C is complete. And these all of these behave quite nicely because first of all we have like a symmetric monoidal localization from growth to growth comp, and then that kind of carries over here. And we have a nice description of morphisms in this two category growth ST comp, which is sorry uh, morphisms in growth ST comp between the following objects. This is given by given by Coleman preserving functors on from SP of C to SP of D. So such that the right adjoins are right the exact up to a shift. I cannot see the pointer here. Uh, I apologize that like my writing in this is quite slow, and I hope that's not a problem uh, with respect to time. So up to shifts, great. So maybe I'll say the next thing verbally, which is that like a morphism between SP of C, comma C to SP of D, comma D is right adjointable uh, if and only if you have that the right adjoint of oh sorry I think I've confused myself. Uh, oh sorry, this is yeah. So the morphisms are just uh, Coleman preserving functors which are right exact of shift. So, I mean, the confusion was because a morphism is right adjointable if and only if the right adjoint is also right the exact upward shift, right? Okay, and the similar like description is follows for like a square being vertically or horizontally right adjointable. So we will now like work with this two category, but like use the notion of an almost rigid algebra from last time, and putting these together is what an admissible algebra is. So an algebra A in Grothcom is admissible if is an almost rigid algebra of Groth ST comp. So I'll just write this out, write what this means. So this means that firstly, the multiplication mark on A, this guy is compact. So so for Coleman preserving functor uh, between objects of growth. So I could have just said morphism and growth. Uh, being compact is the same as the SP of the spectrum of I don't know how you say it. So F is compact if and only if SP of F um, admits Coleman preserving right adjoint. Right adjoint. So this is half of the condition that we want a morphism in Groth-ST comp to be right adjointable. The second condition is now that the right ad, sorry the right adjoint to this guy is right the exact up to a shift. And finally, we have that for an almost rigid algebra, we have these squares that we want to be vertically and horizontally right adjointable, which translates to the following. SP of A tensor A. SP of A. This is both and horizontally right adjointable. Um, right, so this is just like translating what this means, and from this, the following. I mean, it really is a corollary, but like since
Sorry, are there heads
yeah,
missing in the tensor product of the diagram?
Yeah, I was about to say that.
what the completed ones? Yeah. Sorry, this was the question, right?
Yes, thanks.
Yeah. Okay. Thanks. Um, so the theorem now is from is like basically follows from the theorem of last time, which says the following. So let A be an admissible algebra in growth comp, and M be left A module. Then first of all, the action map mu M is not good notation, but we won't use it much, so it's fine, I think. This thing is compact, and secondly, if F from M to N is a morphism of left A modules, uh, such that F is compact and right adjoint to SP of F preserves, sorry, is right, the exact up to a shift. There's a lot of words to write. Then the commutative square given by this morphism from M to N. So you have the action map on the horizontal things, and on the vertical maps you have this thing that's induced by F, right? And this is I should go down. Is both vertically and unjointable, right? And the proof is really like since we know this about almost rigid algebras from last time. This
By the
proof,
way,
like,
sorry to interrupt. Sorry to interrupt.
yeah,
I just wanted to ask, like in the first statement, are you sure like there's no additional? things like shouldn't SP of mu be also right to exact up to a shift? I mean, yeah, the right adjoint of SP mu m.
Oh, yeah. So compactness is equivalent to that condition. Oh, I see what you're saying. Yeah. Uh, oh, yeah. Thank you. Yeah. Sorry. I've just forgotten to write it. Um, yeah. Thanks a lot. I just forgot to write this.
No, you mean the right adjoint of SP mu m.
Yeah. Yes. That's what I mean. Uh, yeah. When I write it up, I just write it more neatly. But so this first condition is saying that like A tensor M defines for you a morphism in Roth ST comp. So translating that will be to say that the action map is compact and the the right adjoint to SP of this guy is SP of mu M. Uh, is the right adjoint of SP of mu M is a rightly exact equation. Yeah. Okay. So is this fine? And are there any questions? Okay, I'll move on then. So we have the following corollary. So before that, so the notation is the following: for M and a pair of um, right and left A modules, where A is, I mean, usually A will be admissible, but like uh, in gross count, this an algebra object. We denote var hat of this would be the bar resolution uh, in gross count. Equivalent, yeah. So equivalently, it's the completion of the bar resolution in gross because this font is symmetric monoidal. So with this, the corollary we have is that same setting, right? I think I ask for A to be commutative. Let A be admissible and Mn is above. Right. The first statement is that every face map of the completed bar complex is compact. And the second thing is every face map of the non-completed one This is almost compact. So the proof is really just a couple of lines. So for one, every face map, yeah,
Uh, s- Sorry. So is it true that this bar hat is the same as the completion of the usual bar?
yeah, I think so.
Okay.
I think it isn't it. It's just a bar construction in graph comp, right? So
Yeah,
just
but
No,
it's also
you,
the completion of
But I think this gives you the same thing.
yeah, I
the.
mean, because it's probably like a column versus like a left the
Yeah,
track.
because the localization is symmetric.
Yeah.
Yes.
Yeah. Where was the yeah? So okay, so back to the corollary. We see that every phase map is some action map of A on an A module, and it so implies that follows from the theorem, because we said that yeah, that was the first assertion of the theorem, right? That like the action map is always compact, and one more condition, but we only care about compactness for now. For the second thing, we do use this interchangeably, that it is the completion and it is the bar construction in graph comp. So this follows from the fact that if C D in graph, C to D uh, is almost compact, if and only if the map from C hat to D hat is almost compact. This is because this is proved earlier, but it's pretty simple. It's because like any the map from C to C hat is an equivalence for n truncated objects for any n, and these almost compact are talking about preserving some colimits when restricted to n truncated objects. So from this it follows that, I mean, and clearly compactness implies almost compactness. So yeah. Right, so this corollary is quite nice because as we will use quite often, almost compact maps are really nice when it comes to taking colimits, in the sense that if you take colimits along diagrams as transition maps are almost compact, then such colimits exist in growth. Uh, so, so the first use of this will be to like finally define a relative tensor product. So the corollary or proposition, whatever, no, let A be commutative algebra, admissible algebra. In Broadcom, then the first assertion is that this category has a symmetric monoidal structure, or is symmetric monoidal. Maybe I should just say is symmetric monoidal with this relative tensor product, which is what I'll be using from now. This will be the realization of the bar complex, of the completed bar complex. And the second thing is if you have a morphism of admissible algebras, then you have that you have a extension of scalars functor, which goes from like so. Then there is an extension. So given by it's just a functor from A modules to A prime modules. Which is basically given by taking the related tensor product with A prime. So M maps to the colimit or delta of the completed bar complex over A with A prime and M. Right. So the proof reduces to this fact about almost compact morphisms I was saying, and I'll just prove this now. So firstly, it suffices to show that the realization exists in Broadcom. And that it commutes with the functor with this functor for all objects C and Groth. Groth comp, I mean, and it's a completed product. And to see this, like to show this statement, we have that we can further reduce to doing everything in Groth because note that Groth comp is a symmetric monoidal and a colimit preserving functor. So it suffices to say that that the realization exists in Groth. So so the realization of the bar complex in Groth exists. And that it commutes with this sort of guy for all. But this is where our previous chronology comes in, but all the transition maps, so all the face maps in face maps of the bar complex are almost compact. And we use this fact that was done earlier in the seminar, and Groth AC, which is the subcategory of Groth consisting only of the almost compact morphisms. This contains all, rather admits small colimits, which is preserved by its inclusion into Groth. And the following composite. So this is I didn't note down the number, but yeah, this is from the first section of the paper. So this is a fact we will be using commonly because most of our diagrams that we want to consider colimits of will be something like this bar resolution, and like almost compactness is like a really nice condition because of because of the exact result. No pun intended. So now we've shown that like we have a tensor product. So the next goal and this probably the next thing and the only other thing we'll be talking about is how these guys interact with limits and colimits. So this relative tensor product interacts with limits and colimits. So first of all, a morphism of left A modules into M prime is compact or almost compact or left exact if the underlying growth and decrease stable categories is as is what you would expect. So the first result pertaining to these is that the relative tensor product sort of preserves both of these by both I mean almost compactness and left exactness. So the relative tensor product preserves both of these properties of morphisms. So let A be an admissible commutative algebra in gross comp. And FB as above, right? F from M to M prime be a morphism of A modules, and let N be any A module. So the first thing is if F is compact, then this guy from is almost compact. Oh, and secondly, if F is left exact, then F tensor ID is left exact. So recall that we have this property, both of these properties in Groth, which is say that if you have a morphism of Groth and equally stable categories, which is almost compact or left exact, the corresponding property holds whenever you take the tensor product with any other object of Groth. So we will use this, and we will use like the nice behavior of the bar complexes once again. So I mean, these are actually two. The proofs are very quite different, but like I just clubbed them because the rest of the statement is the same. So for the first part, we have the following morphism from the maybe this guy. And this is all facts. This it's a level-wise almost compact morphism whose transition maps are like which are in this case phase maps uh, are also almost compact. To see that it's level-wise almost compact, this is the fact that I stated verbally, which is that C to D in cross AC implies that C or tensor E in process AC is any object in Groth. And the phase maps being almost compact is this corollary we've now already used a couple of times. Right. Okay, so but like again, this since the functor from Groth to Groth comp is like nice enough that like it's symmetric monoidal and it preserves colimits, we can just like uh, make the corresponding statement for the uncompleted bar complex. So we can consider bar Fn, right? And since it's using the same fact now, since Groth AC admits all small colimits, the realization of bar Fn exists, and that is also almost compact. So let me say then the realization of bar Fn is almost most compact. And further, yeah, and this like since the functor from growth to growth comp is again nice, we can move back and then say that this implies that the completion of this the realization of this completion is also almost compact. Yeah, and I think that then we're done. This is what we wanted to show.
Maybe as a short comment.
Yeah.
So I think I just looked at how it's written up in the paper, and so Stefanich writes it slightly differently, and I think the reason is that you need to be a bit careful with Groth AC, because this thing does not have. I mean, I don't think this gets a symmetric monoidal. It's like some sort of like symmetric monoidal structure, I think. So you need to be. I mean, you need to be a bit careful.
Oh,
So
right,
I
okay.
mean, this only
Yeah.
gets a symmetric monoidal structure if everything is complete. So somehow.
Okay, then
No,
then
I think the argument still works, but you just have to be like
yeah.
somehow like slightly more careful what is like actually complete here. Because if M and N are not complete, then somehow, I mean, if they are complete, then I think you can just write down what you did. But if not, then like yeah. But in like overall, I think you just go via the uncompleted bar complex and then complete at the end, and then this just works. But,
Yeah. Yeah, that's a
but
good
I
point.
think
But like it works out because the inclusion from Groth almost complete to Groth preserves Coleman's.
yes. So I agree. I mean, I think the argument is correct, but somehow like you need to just be a bit careful.
Yeah.
Okay, thanks.
Okay. So we have a similar statement about left exact for F left exact, which is like this bracketed statement. So again we consider first the bar complex in Groth. Right, and so now bar Fn. So recall that like this in the second part we assume now that F is left exact but not almost compact. So bar Fn dot from the bar complex is level-wise left exact, and the transition marks are again almost compact. And I'll just write this. It's because there is an analogous statement about left exact morphisms. So a morphism in Groth is left exact. Implies that whenever you tensor with a new guy, that is left exact as well. So this is why it's level-wise left exact. Is left exact. And now we cannot like use the previous thing because of course that was about almost compact morphisms, but at some point there was like what I probably think that's the most technical part of the paper I've seen up to this point, which is like this weird lemma about like you having a diagram in two variables and some of these guys being almost compact and some of these guys being left exact, and then you make a statement at the end. I'll write like a paraphrasing of this, but before I do that, I'll say that it suffices that to show that like the following squares. Oh, I should put this anywhere. Yeah. So the following squares. Where the horizontal maps are given by face maps. This every such square is maybe I put this in brackets is horizontally right adjoint. So once, if you believe me for now that it suffices to say this statement, um, this is just the theorem above because, so let me scroll up. It's the second part of this theorem here. So because each of the horizontal maps are again action maps, and the vertical maps are uh, given by the like induced by this functor from M to N. This where is the pen? Um, So as for the suffices to say thingy, we have this really long lemma or proposition.
Swami,
Yeah,
sorry to interrupt. Like,
yeah.
do you think, I don't know, shouldn't, so you said that you used the last term. Shouldn't this be completed? Like the bars?
No,
Um,
I think I'm making them all in Groth, and then like at the end I will complete it.
okay. Sorry. Yeah, thanks.
Yeah. I mean, okay. So before I say why star, what star is, uh, uh, now that you have this, now you have that bar Fn from bar Mn, this is all over A, to bar M prime N is, oh, wait. I want to say that the realization of this. So the realization of this is left exact. Yeah. And right, I'm a little unsure about this last sentence, so I can't think about it right now.
I think we
Um,
proved. I think we proved like a couple of weeks ago that if I have a left exact morphism and then take the completion, I'm still left exact.
Oh, okay, great, okay.
Yeah.
Yeah, thanks. Because
Yeah, also I think we're using that completion commutes with colimits here, but
yeah,
that's just as
so
an
as
example.
this completion commutes with colimits and reflects left exactness. Okay, so now for this star. So
I'm
there's a
not sure it
couple of
actually. I'm sorry, I'm not sure it actually reflects legs, but like the things that we need it does.
yeah, sorry, I mean
No, I think it does
yeah,
both. It does both. It both preserves and reflects. I think this was some proposition earlier.
Wasn't
Yes,
that
it does
for almost
both.
compact? Oh, then I'm sorry.
No, yes, it's for left exact and almost. It both reflects and preserves left
Yeah.
exactness and almost compactness.
I see. Okay,
Yes, but I think here you're using preservation, as Alex
yeah,
mentioned.
sorry. So yeah, thanks for that. So as for the missing part is from these two propositions, which I will like roughly like paraphrase. So given a diagram make two variables into graph where uh, for alpha prime in I and beta prime in J, uh, f of alpha beta to f of alpha beta prime. This is left exact. And on the other variable, you have that f of alpha beta to f of alpha prime beta is almost compact. So I should probably say here that for for uh, for any alpha, like these indices, this happens. And you also have that certain square, the square given by both transitions, alpha beta prime, alpha prime beta to alpha prime beta prime. This is sorry, horizontally weighted jointable. Or in brackets, I mean, rather long, like a reference, but equivalently, the third condition can be stated as SP of this square being being horizontally right, adjointable. And the equivalence here comes because equivalently because vertical maps are almost compact, I think. Yeah. Have I written this wrong? No. Vertical maps are almost compact. Tell me if I'm stating this wrong, but like it follows either because the vertical ones are almost compact or the horizontal ones are left exact. So either way, these two propositions are like what we need, because in our case, I is just like I has two objects which correspond to, so f of I will be either m or m prime, and j is like the is delta up here. So so whenever we have that, these these sort of squares are horizontally right adjointable. Uh, since our other two conditions are satisfied, namely that like when we transition from M to M prime, we have a left exact morphism, and when we look at the transition maps of the bar complexes themselves, they have almost compact morphisms. Uh, yeah, then showing that these squares are horizontally right adjointable will say that like when you move to the code, I realize I haven't stated the result of the proposition. Then F alpha to column, sorry, the column of F alpha beta along beta to the column of F alpha prime beta is left exact. Yeah. All right. So are there any questions up to this point? So far we showed that this relative tensor product exists, and uh, whenever you take this tensor product with a almost compact or a left exact morphism, these are preserved. Okay, I'll move on then. So the last couple of statements is that we say something about the limits and colimits and how they interact uh, with this relative tensor product. So as you probably expect now, the theme of the colimit statement will heavily involve almost compact um, transition maps. So More precisely, let A, B, and relative algebra in Broadcom and more A, Broadcom, AC, denote confidence. So we have an analogous statement as that we have had about growth AC, which is that the modules over A, the category of modules over A admits all small colimits and inclusion into and the forgetful functor to Grothcom. Oh, so this is not Grothcom. Sorry. And secondly, we have that it commutes when we restrict to almost compact morphisms. This thing commutes with taking this relative tensor product. So for every E in uh, composite from reserve small colimits. Reserves, well, so yeah, colimits. So I'm running out of time, but the proof is like so for the first part, it's literally a proposition of Lurie. So we use that. We have this analogous fact for without the mods there. So then this following this proposition from higher algebra. Corollary 4, 2, 3, 5. And this literally tells you that like if you have a colimit, if you have a diagram into this module category such that like when you project down to Grothcom and that thing when you project down to Grothcom, tensoring with any C in Grothcom preserves colimits, then the sorry, no, I should not try to paraphrase this. So the statement is, I'll say this verbally, if M is an infinity category that is left tensored over a monoidal infinity category C, and A is a algebra object in C, then if you have a diagram into left modules over A, such that whenever you project down to M and then take its composite with any object C, uh, that thing is a colimit diagram. That means that like your thing upstairs in the module category is a colimit diagram as well. So yeah, I, I feel like I should not have said that in words because it's a lot of words, but it's quite literally from this statement of higher algebra. And for 2, we may reduce to the following, to showing that where is this? If C is a colimit of C alphas, then when you look at this guy, this is the colimit of uh, the corresponding guys. And by reduce, I mean we use the same corollary of higher algebra. And for this, it is enough to show that so this completed tensor, the relative tensor product is a realization. So if we show that the left-hand side is a colimit on each stage of this simplicial diagram, then it follows that the realization will be because they're all colimits that's involved. So it suffices to show that the tensor product with bar. Okay, maybe I skip a step here, and I'll say that we first look at everything in Groth, not in Groth comp, so that like the almost compact this statement about almost compact morphisms behaves well, and then in the end we will take completions of everything. So we want to show that the tensor with this guy is the colimit of the tensor with right, and this follows about from the same fact about namely that it admits colimits and then taking the tensor product with any object in Groth preserves these colimits. So yeah, so this statement about the colimits is essentially like just bootstrapped from the corresponding statements about Groth comp with the help of this corollary from Louis. Right, and I have 15 minutes, which should be enough. And next, and finally, we will talk about how limits interact with these guys. And for limits, you may guess that the setting is not almost compact, but left exact morphisms. So that so before I write this, is there any questions about the previous one? Do you like me to repeat something? Okay. So for the last proposition, we have that once again we work with an admissible commutative algebra in Groth comp. and let m equal to limit alpha be a limit diagram with left exact transitions, and let n be an A module. But unlike the previous case where the column is just commute, we have an additional assumption, which is that such that the spectrum objects of n form sorry are dualizable as an SPA module in stable presentable categories. Then we have that the limits commute. So we have that M relative tensor product with N, the morphism from this to the limit of these guys is an equivalence. Right. So before I start talking about the proof, I should say that this limit exists because there's also a fact from earlier, which is that on the subcategory of Groth, which is denoted Groth left exact, whose morphisms are only consist of left exact morphisms. In this category, this admits all small limits. And okay, since I'll also use it in proof, I'll just write it. So Groth Lex admits small limits, and this is preserved by the following chain. Right? Oh. I think I want count here. So in particular, the localization from Groth to Groth-com preserves limits with left exact transitions. So since you have a diagram which already has left exact transitions, this limit makes sense and it exists. So we want that the relative tensor products of M with N this is an equivalence. But the functor from Groth to Groth-com preserves so it suffices to like talk about the uncompleted ones. Where's the Now we make a couple of further reductions. So further, it suffices to say that this is an equivalence after applying the functor after looking at spectrum objects. So I think this follows from a remark from a remark in section 2.1, which says that when you have C, which says that if C is the limit of A alpha with Lex transitions, then the connective objects of SP of C correspond to those all SP of CAs. So this allows us to further just prove our statement about the spectrum objects, and this is now possible because of our assumption on n. So now this with the canonical map from spectrum objects of M to the limit but this is an equivalence because n is dualizable. No, sorry, not n. Spectrum objects of M is dualizable. Right. So that finishes everything I want to say. So in conclusion, this is a bunch of technical things, but we showed that for an admissible commutative algebra, we can define relative tensor products, and that these behave nicely with colimits along almost compact maps, and sorry, this behave well with colimits along almost compact maps and limits along left exact transition maps. So yeah, that I think the next talk is to uh, the lack of examples in this is because the next talk is just about an example, which is QCO X CN, the connective part of this. And yeah, that's all I have to say. Thank you.
So let's thank our speaker, and then we're open to questions, I guess. Okay, so if there are no questions for the recording session, we'll stop recording and we can move to the post-recording session. Thanks.